Every complex machine you see, from a massive jet engine all the way down to the phone in your pocket, it's all built using a kind of secret language. And today, we're going to decode it. We're talking about a universal standard called BS 8888. Have you ever really stopped to think about how a modern car is even made? The engine might be built in Germany, the electronics could come from Japan, and the body panels from the US. So how is it even possible that when these thousands of parts meet for the very first time on an assembly line, they fit together perfectly? We're talking precision down to the width of a human hair. Yeah, because in the world of engineering, close enough just doesn't cut it. It's not an option. A single bolt that's off by a fraction of a millimeter, or maybe a gear that isn't perfectly smooth, well, that can lead to catastrophic failure. So, how do engineers all over the globe pull this off and avoid disaster? Well, they do it by using a universal language. It's a set of rules so incredibly precise that an engineer in, say, one country can send a single drawing to a factory on the complete opposite side of the planet, and they can be totally confident that the part that comes back will be an exact match. It's pretty amazing when you think about it. And that language, that rulebook, is BS 8888. It's the official British standard for technical drawings. And let me be clear, this is not just a set of friendly suggestions. It is a comprehensive, detailed rulebook. It literally covers everything, from the exact shape of a tiny screw thread to the required texture of a finished surface, the whole shebang. And the impact of this, it's absolutely huge. When everyone's speaking the same engineering language, designs are understood perfectly, right? This massively cuts down on errors, which saves a ton of time, money, and materials. It's what makes global collaboration even possible. And, most importantly, it leads to safer, more reliable products, the stuff we all depend on every single day. All right, so what does this language actually look like in practice? Let's dive in and start with one of the most fundamental concepts, dimensioning. Okay, so at its most basic level, dimensioning is all about adding numbers to a drawing. Sounds simple, right? But it's so much more than just slapping a label on how long something is. It has to define every single feature, from the simplest straight line to the most complex winding curve. And when I say every feature, I mean every feature. The length, the width, the diameter of a hole, the angle between two surfaces, the radius of a curve, all of it has to be explicitly defined. There is absolutely zero room for guessing or ambiguity. This is the only way you can guarantee that a part from one factory will fit perfectly with a part from a totally different one. Okay, but here's where it gets really interesting. It's kind of paradoxical, actually, because in the real world, perfect manufacturing is impossible. It just is. No machine on Earth can create a part that is exactly 30 millimeters long every single time without fail. There will always be tiny variations. So how does this language of absolute precision deal with real-world imperfection? This is where the genius comes in. It's through a concept called tolerancing. See, instead of demanding impossible perfection, engineers do something much smarter. They define an acceptable range of imperfection. So for every single dimension on a drawing, they specify the permissible limit of variation. Just look at the difference here. A simple drawing could just say 30 millimeters, but with tolerancing, it gives a range, say, for example, somewhere between 30 and 30.03 millimeters. Now, any part that measures within that tiny, tiny window is acceptable. It passes the test. And suddenly, you're not just defining a size anymore. You're defining a standard of quality. Okay, so we've got dimensions and we've got tolerances. But to make everything even more efficient, and honestly, to keep the drawings from getting totally cluttered with text, BS 8088 uses this rich vocabulary of symbols. Think of it like a kind of engineering shorthand. Let's take surface lay, for example. It sounds complicated, but it's really just the direction of the tiny tool marks that get left on a part after it's been machined. Now, instead of writing out a whole sentence explaining that, a simple symbol does the job. An equals sign could mean the marks have to run in one direction. An M might mean they can be multi-directional. It's amazing. One little symbol instantly communicates a complex manufacturing instruction. No confusion. Let's make this a little more real. Here's a perfect example. We're looking at how you join two metal plates together using a super common technique. It's called a single V butt weld. And on an engineering drawing, that entire complex instruction, it gets reduced to just one single symbol, the letter V. That's it. That is the power of this language. It is so clean, it's fast, and it's instantly understood by any welder or engineer on the planet who knows the standard. And believe it or not, it gets even more powerful than that. A single symbol for something like surface texture can carry a bunch of different instructions all at once. Different spots around the symbol can specify the required roughness, the manufacturing method, like whether it should be ground or milled, and even the direction of those tool marks we just talked about. It is an incredibly dense and efficient way to pack a ton of information into a tiny space. All right, so we've looked at dimensions, tolerances, and these cool symbols. Let's zoom back out to the big picture. Why is a rule book like this not just, useful, but why is it absolutely essential to our modern world? Well, think about it. Without a standard like this, what do you have? You've got ambiguity, you've got misinterpretation that leads directly to errors, waste, and just total confusion. It would make global collaboration pretty much impossible. But with the standard, you get the complete opposite. You get clarity, precision, and efficiency. It really is the invisible framework that makes all of modern global engineering possible. And let's be really, really clear about the stakes. This isn't just about making parts fit together nicely. When you're manufacturing something like an aerospace component, failing to comply with the standard doesn't just risk a financial loss, it literally risks lives. This language is a critical, non-negotiable part of the safety chain. So, when you boil it all down, BS888 is so much more than just some dried technical document. It's one of those invisible protocols quietly humming in the background that enables our modern, interconnected world to even function. And it kind of makes you wonder, doesn't it? What other invisible rulebooks are out there, precisely and silently running the systems we all rely on every single day?